How I do this? So
Good boy. What's got you down?
this darn physics problem. I don't
Let me take
know.
a look at that.
Don't know how to do it.
It's not about that, Brendan. It's about F equals MA.
What's F equals MA?
Here, let me spell it for you. Give me a beat.
That's a nice beat.
F is for forces, that's not an object. M is for mass of that object. A is for acceleration or rate of change of velocity down here on this great big earth.
Wait. Wow.
AMX. Hello, Fernando.
Hello. Newton's second law states that a body of mass m, subject to a net non-zero force F, undergoes an acceleration a that has the same direction as the force and a magnitude that is directly proportional to the force and inversely proportional to the mass. Hence, a equals F over m, or as we more commonly know it, F equals ma. You stay classy, San Diego.
This fundamental concept of physics is applicable to every aspect of life, ranging from sports to space shuttles. However, in order to master the formula, one must understand certain rules. For example, one must understand the units behind each aspect of the formula. A, or acceleration, is in meters per second squared, which of course comes from the fact that acceleration is a change in velocity, which is in the units meters per second, over time, which is in the units of seconds, which when combined yields meters over seconds squared. Mass, or m, in the formula is in kilograms, which is essentially the amount of matter of the object, or how much it resists the acceleration. Lastly, these two units, when combined, yield kilograms times meters over seconds squared, which is known as the Newton, which is the unit for the force that is applied. Take it to the bank.
Additionally, one must understand that it is the force, which is a push or pull, that causes the acceleration, for an acceleration cannot cause a force.
Lastly, one must see that the acceleration only applies as long as the force applies. For example, throwing a ball. By the time the ball leaves your hand, it is no longer accelerating in the x direction at all. It is only accelerating in the y direction due to the force of gravity applied at the Earth's surface. You, Emil.
Hello there. This understanding of the basic principles of Newton's second law allows for the comprehension of more complex versions of his law, namely the F net equals ma observed per plane formula. In addition, weight equals mass times gravity.
By applying the formula F equals ma, we can solve such complex problems as finding the acceleration of a pulley system with masses connected on either end.
First, you must set a direction of motion. Because the heavier mass is on this side will be going in the downward direction, while this one gets pulled upwards. Then, you must determine the forces acting on each block. On the block of one mass, there will be a force acting, mg, pulling it downwards, and tension, pulling it upwards. So, you plug that into the formula of F equals ma. You have tension, which will be the stronger force because it's pulling it upwards, minus mg, pulling in the opposite direction, is equal to that mass. And this is the block of 1. And then on the other block, that will be the same thing. mg pulling downwards with tension pulling upwards. However, for this block, the mg will overcome the tension because it is moving in a downward direction. Therefore, you must solve for tension because tension is the only variable that is the same in both equations. So, tension is simplified as m1a plus m1g. So when you plug that in for tension on this, you get M2G minus M1A plus M1G is equal to this is a minus, sorry, is equal to M2A. And when you plug in the variables we're assuming G is equal to 10 for simplicity. You plug this in, M of 2 is 2 times 10 minus M of 1 is 1 times, that's the acceleration, plus 1 times 10 is equal to 2 times A. So when you simplify that, you get 20 minus A minus 10 is equal to 2A. Then you bring the A over and simplify this side, so you get 10 is equal to 3A. Then when you divide the 3 over, you get that the acceleration is equal to 10 over 3. And that's your answer, all using the formula F equals ma. Oh, and the acceleration is in meters per second squared.
So we, as the observer, are stationary, and Emil Nelson is moving at great speed right now, a little too fast, and since we are stationary, it appears as though he is accelerating very fast. But on the other hand, when we accelerate with Emil, he does not seem to move as fast, as demonstrated here. Now, he appears to be moving he appears to be stationary, just with us. But relative to the ground, he is actually moving fast.
Huh.
Isn't that dandy?